This is Dr. Anitya Raj welcoming you for one more session in coordination chemistry. In this session, we shall see the very important topic, the postulates of valence bond theory. Okay, let us see the postulates one by one. Actually, this theory, valence bond theory, that is VBT, was proposed by Linus Pauling, and it's also referred to as Pauling's theory. Okay, so let us see the first postulate now. The ligand and the metal bond, the ligand metal bond in complex is covalent in nature, formed by the sharing of electrons between the metal and the ligand. Okay, so let me write an example for this. Coordination complex, nickel CO 4 times. Okay, so this is a coordination complex. So now what's given in the first postulate is the ligand metal bond in complex. See, there will be a bond between the ligand. See, this is ligand, CO 4 times, it's the ligand, and nickel, it's the central metal atom. So a bond between will be there, between this ligand and the metal atom, and that bond will be covalent in nature. Okay, and this covalent bond will be formed by the sharing up of electrons. So electrons will be shared up between the ligands and the metal atom. So because of that, a covalent bond will be formed. Okay, that's the first postulate, right? So what's the next one? See, each ligand should have filled orbitals containing lone pair of electrons. Okay, so this ligand, okay, each ligand, here we are having 4 ligands, is it not? CO is the ligand, and we are having 4 ligands now. So these ligands should have filled orbitals, and those orbitals should contain lone pair of electrons. Okay, it should have lone pair of electrons, right? The next postulate is the central metal atom or the ion provides a number of vacant orbitals in order to accommodate the electrons donated by the ligands. See, it's given already that number of vacant orbitals which this central atom is going to provide should be equal to its coordination number. Okay, understood? See, the central metal atom should provide some vacant orbital. For what purpose? In order to accommodate the electrons donated by the ligands. See, already it was given, right? See, the ligand is going to donate the lone pair of electrons, right? Those lone pair of electrons should be accepted by the central metal atom. If so, this central metal atom should have some vacant orbitals. And how many number of vacant orbitals this central metal atom should have? It should be equal to its coordination number. What do you mean by coordination number? It's a number of ligands attached to the central atom. Okay, see, if we are taking this complex, four ligands are there, so 4 ligands will be attached to the nickel atom. So what's the coordination number of this complex? It is 4, right? So according to this postulate, this central metal atom should have 4 vacant orbitals in order to accommodate the lone pair of electrons donated by the ligands. Understood, students? Okay, so let us see the fourth postulate, or the fourth metal atom undergoes hybridization to form vacant hybrid orbitals. Okay, it will be forming vacant hybrid orbitals, right? So as I told you earlier, the central metal atom should have some vacant orbitals to accommodate or to receive the lone pair of electrons donated by the ligands, right? So this vacant orbitals will be undergoing hybridization. Actually, the vacant orbitals of this atomic orbitals of the central metal atom or the ion, according to the requirement, it undergoes a certain type of hybridization. Okay, during this hybridization, these orbitals mix up together. Okay, so because different orbitals will be having different energies, right? So but we are in need of hybrid orbitals of same energy. Okay, so during hybridization, these orbitals mix up together and redistribute their energies. Okay, on account of this mixing, the same number of hybrid orbitals of equal energy will be obtained. Understood? So hybridized orbitals of central metal atom or ion linearly overlaps with filled orbitals of ligands to form coordinate covalent sigma bond between the ligand and the metals. Understood? So as I told you earlier, this central metal atom will be undergoing some hybridization, and it will be forming a vacant hybridized orbitals. Okay, this vacant hybridized orbitals will be undergoing linear overlap with the filled orbitals of the ligands, okay, and to form the coordinate covalent sigma bond. So what type of bond is formed? A coordinate covalent bond due to sharing up of electrons between the ligand and the metals, okay. So this actually what happens is when this ligand approaches the central metal atom or the ion, the vacant hybrid orbitals of the central metal ion overlaps linearly with the orbitals of the ligands, okay, containing the lone pair of electrons and form a strong ligand metal coordinate covalent bond. Understood? So that's the point given here in the fifth postulate. Okay. So in the case of octahedral complexes, the n-1d orbitals will be there, and this orbitals will be involving hybridization and forms inner orbital complexes. See, this inner orbital complexes are otherwise called as low spin complexes or spin paired complexes. Okay, let me explain this now. See, this 3d orbital, this is 3d orbitals, okay, and this is 4s and 4p, and here we have again 4d, okay. So in the case of n-1d orbitals, okay, so let this one n-1d orbitals, see here n-1d orbitals, here these all these will be completely filled, okay, these 3 orbitals will be filled, okay. So this will be vacant, okay, this will be the vacant hybrid or hybridized orbital. So this will be taking up the orbital, these orbitals will be undergoing hybridization, okay. So what's this? See here d2, how many d orbitals have been taken? 2 d orbitals, 2 d2, then 4s, is it not? So d2, yes, and then how many p orbitals? 3, is it not? P orbitals 3, right? So 3 p orbitals has been taken and 1 s orbital and 2 d orbitals. So d2 sp3. So these the inner d orbitals are involving in hybridization. Understood? So inner d orbitals, it's not taking up this 4d, but inner d orbitals are involved. So 2 inner d orbitals, 1 4s and 3 p orbitals been involved, okay. That's why it's called as d2 sp3 orbitals. So the complexes involving this d2 sp3 hybridization are referred to as inner orbital complexes. This is because the formation of such complexes involves the participation of this inner d orbitals, okay, that is n-1d orbital of the central metal atom or the ion during hybridization, okay. So these complexes have lesser number of unpaired electrons, therefore they are also called as low spin or spin paired complexes, okay, low spin or spin paired complexes, okay. So that's why. So I can give octahedral complexes Fe Cn6 4 minus, okay, and another example is CO NH3 6 3 plus, okay. I can explain all these things, inner octahedral complex, inner orbital complexes and outer orbital complexes, when I am dealing with these topics after finishing this VBT, okay. So that you can get a clear cut idea. Let us see the next postulate. In octahedral complexes, ND pattern, okay, ND orbital involves in hybridization and forms outer orbital complexes or high spin or spin free complexes, okay. So the complexes which involves the sp3d2 hybridization are called as outer orbital complexes. Understood? This is because this involves, okay, see here, this involves the participation of the outer d orbitals. It involves the participation of outer d orbitals, that is nd orbitals of the central metal atom or the ion during hybridization. This outer orbitals, okay. Such complexes possess comparatively higher number of unpaired electrons, okay. But in the previous one, we will be having paired electrons, but here we will be having higher number of unpaired electrons. Therefore, they are also called as high spin complexes or spin free complexes, okay. See here how the hybridization takes place. See, this 4s will be getting involved, this 4p, and then here from here 2d, okay. 2d orbitals will be involved, okay. All these will be paired up, these will be paired up, so that the orbitals which are involved in this hybridization will be 4s, 4p and 4d. So 1 es, is it not? 3p, p3 and d2, right. So let me give an example for this type of complexes. So Fe H2O 6 times, okay. 2 plus. Okay, this is an example for this category, right? So again, I'll be explaining all these things in my next video. So that orbitals are directional in nature and their orientation in space gives a definite geometry. Okay, so all these hybridized orbitals will be directional and they will be having some certain orientation, and with that we will be having some definite geometry. Okay, see here, if the coordination number is 2, then the hybridization pattern will be SP. Okay, SP, and the geometry will be linear. So these are all the examples coming under linear geometry. Next, if the coordination number is 3, we will be having SP2. Okay, that is trigonal planar. If it is 4, it is SP3, we will be having tetrahedral. Again, if the coordination number is 4, we will be having next pattern, that is DSP2, that is square planar. Okay, and like if the coordination number is 5, then DSP3, okay, trigonal bipyramidal, right? So the next category, likewise we are having the for different coordination number, different hybridization will be there and different geometry will be there. Understood, students? See the next postulate, a complex is paramagnetic if it contains one or more unpaired electrons. Okay, during hybridization, if the orbitals are having one or more unpaired electrons, then we call that complex as paramagnetic in nature. But in the same case, if all the electrons in the complex are paired, if they are paired, then the complex is diamagnetic. If it contains an unpaired number of electrons, then we call that complex as paramagnetic, and if the complex all the electrons are paired up, then the complex is diamagnetic in nature. Okay, so the next postulate goes like this: during complex formation, the Hund's rule of maximum multiplicity is strictly followed. What's Hund's rule? So its Hund's rule states that if 2 or more orbitals of equal energy are available, then the electrons will occupy them singly before filling them in pairs. Okay, so that means if 2 or more orbitals of equal energy are available, then the electrons will be occupied singly instead of getting paired up. Okay, that's given in Hund's rule. Okay, so based on the Hund's rule, the electrons will be arranged. Okay, but however, the influence of strong ligands, the electrons may be forced to pair up against Hund's rule. If the complex is having strong ligands, automatically the electrons will be getting paired up, okay, against Hund's rule. Okay, so according to Hund's rule, the electrons will be arranged singly instead of getting paired, but in the presence of strong ligands, the electrons will be forced to get paired up. Okay, that's the meaning of this postulate. Okay, I'm going to give some examples for strong ligands. See this carbonyl CO, it's a strong ligand. Cn minus, it's a strong ligand. For weak ligand, F minus, Cl minus, Br minus, I minus. Okay, then SCN minus, okay, SCN minus, then S2 minus. All these are examples for weak ligands. Okay, some ligands will be acting as strong as well as weak. So let me give example for this: NO2 minus, then ethylene, okay, Cn, then H2O aqua, then amine NH3, okay, then EDTA, right, EDTA4 minus. All these are can act as either strong or weak ligand depending upon the complex. Okay, so according to last postulate is greater the overlapping between the ligand orbital and the hybrid metal orbital, greater is the strength of the bond. Understood? So if the overlapping is perfect, or if it is very strong, or if it is greater, automatically the ligand orbital and the hybrid metal orbital will be getting overlap perfectly and the strength of the bond will be greater. Understood, students? So these are all the important postulates of valence bond theory, right? Fine, students, you might have understood all the postulates of valence bond theory. We'll meet you with another important topic in my next video. Until then, it's Dr. Anita signing off from you. Thanks for watching.